There is a world, not so far from our own, that once knew the sound of water, not the whisper of ice melting in sunlight, not the hiss of vapor escaping into vacuum, but the full-throated roar of rivers carving through stone, the patient lapping of waves against ancient shores, the thunder of rain falling from clouds that stretched across an entire hemisphere. That world is Mars, and if you could have stood on its surface 4 billion years ago, you would not have recognized it. The Mars we know today is a monument to silence, a desert planet wrapped in dust and cold, its sky the color of rust, its surface sculpted by wind and time into a landscape of haunting desolation. It is beautiful in its own right, but it is a beauty born of absence, of what has been lost. But there was a time, in the deep history of our solar system, when Mars was something else entirely. Scientists call this period the Noachian Epoch, named after Noachis Terra, one of the most ancient and cratered regions still visible on the Martian surface. It began roughly 4 billion years ago, not long after the planets themselves had finished forming from the disk of dust and gas that once surrounded our young sun. And during this epoch, Mars was alive with possibility. We know this not from speculation, but from evidence. Evidence carved into the bones of the planet itself, written in stone and sediment, waiting for us to read it. Consider Jezero Crater. Today it's a shallow bowl of rock and dust, 45 kilometers across, sitting on the western edge of a vast impact basin called Isidis. The Perseverance rover is there now, grinding samples from boulders, analyzing the chemistry of pebbles worn smooth by forces that no longer exist on Mars. But 3.5 billion years ago, Jezero was a lake, not a puddle, not a temporary pond left behind by melting ice. A lake, deep enough to persist for millions of years, fed by rivers that flowed down through the crater's western rim, carrying sediment from the highlands beyond, building deltas layer by patient layer. We can see those deltas still, frozen in time. Mineral deposits that fan out across the crater floor in patterns that are unmistakable to anyone who has studied Earth's river systems. The same physics that shape the Mississippi Delta shape the deltas of Jezero. The same patient work of moving water, sorting grains of sand and silt by size and weight, building landforms that can survive for eons after the water itself has vanished. And Jezero is not alone. Gale Crater, where the Curiosity rover has been exploring since 2012, tells a similar story. At the center of Gale rises Mount Sharp, a mountain of layered sedimentary rock 5 kilometers high. Those layers didn't form in dry conditions. They're the fossil record of a lake that existed for perhaps tens of millions of years, slowly filling with sediment until it created a mountain from its own accumulated memory. Everywhere we look on ancient Martian terrain, we find the signatures of water, valley networks that branch like the veins of a leaf, carved by rainfall and runoff, deltas where rivers met standing bodies of water, lakebeds where fine sediments settled in horizontal layers, undisturbed by currents, testament to stillness and depth. This wasn't a planet with a few scattered oases. This was a planet with a hydrological cycle. Rain fell from clouds, water flowed downhill. It pooled in lowlands and basins. It carved channels through rock. It transported sediment across hundreds of kilometers, sorting and depositing and reshaping the surface in ways that only liquid water can. But water alone is not enough to explain what we see. Water cannot exist as a liquid on the Martian surface today. The atmosphere is too thin, the pressure too low. Any water exposed to the modern Martian environment would either freeze solid or sublime directly into vapor, skipping the liquid phase entirely. For ancient Mars to have had rivers and lakes, and perhaps even seas, it needed something that the modern planet has lost. It needed air, not just any air, a thick atmosphere, dense enough to raise the surface pressure, to trap heat, to allow water to exist in its liquid state for more than a fleeting moment. And the evidence suggests that Mars once had exactly that. We can read it in the isotopes of noble gases trapped in Martian meteorites. We can infer it from the erosion patterns that speak to wind and weather operating on a scale the modern planet cannot support. We can calculate it from climate models that work backward from the geology, asking what kind of atmosphere would be required to produce the Mars we see preserved in ancient stone. The answer is an atmosphere perhaps 10 to 20 times denser than what remains today. Not as thick as Earth's, but thick enough. Thick enough for greenhouse warming, thick enough for a stable water cycle, thick enough to blur the stars at night and paint the sky something other than the perpetual twilight pink it wears now. But even a thick atmosphere is vulnerable in ways that Earth's is not, because Mars had something else in those ancient days, something invisible but essential, something that made all the difference between a world that could hold on to its air and a world that would slowly bleed it away into space. Mars had a magnetic field. Deep in its molten core, currents of liquid iron churned and flowed, generating a planetary dynamo, a magnetic shield that wrapped around the entire world like an invisible cocoon. We can still see traces of it, frozen into the most ancient rocks of the southern highlands, magnetic minerals aligned in patterns that point to a field strength comparable to Earth's own. That field did more than deflect compass needles. It deflected the solar wind. Our sun is not a gentle neighbor. It constantly exhales a stream of charged particles, protons, and electrons moving at hundreds of kilometers per second, a relentless wind that would strip away any atmosphere not protected by a magnetic barrier. Earth has such a barrier. Venus, with no magnetic field of its own, survives only because its atmosphere is so thick and its gravity so strong that it loses material slowly over billions of years. Mars, smaller and with weaker gravity, needed that magnetic shield, and for a time, it had one. For a time, the early Martian atmosphere was shielded from the worst of the solar wind's erosive power. Heat from the planet's interior kept the core molten and the dynamo spinning. The air stayed thick, the water stayed liquid, the planet stayed warm. How warm, we're still debating. Some models suggest a Mars that was only intermittently wet, warming during periods of intense volcanic activity that pumped greenhouse gases into the air, then freezing again when the eruptions ceased. A world that cycled between ice and thaw, its liquid water appearing in pulses, temporary and precious. Other models paint a different picture, a Mars that sustained liquid water for hundreds of millions of years continuously. A world with a stable climate, perhaps not as warm as early Earth, but warm enough. Warm enough for rain, warm enough for clouds, warm enough, potentially, for something even more remarkable. Warm enough for life. That's the question that haunts every image we receive from Mars, every measurement, every analysis. Because if early Mars had liquid water, and a thick atmosphere, and a magnetic field protecting it from radiation and warmth, and time measured not in years but in millions of years, then it had the ingredients. The same ingredients that gave rise to life on Earth. We don't know when life began on our own planet. The oldest definitive fossils are perhaps 3.5 billion years old, but many scientists suspect life arose much earlier, perhaps as far back as 4 billion years ago, almost as soon as the Earth's surface cooled enough to allow it. If that timeline is correct, then life on Earth and the wet epoch on Mars overlapped. They were contemporary. Two worlds, neighbors in space, both with oceans, both with atmospheres, both with the chemistry and energy needed for biology to take its first tentative steps. It's not proof, of course. Mars might have had water and air and warmth, and still remained sterile. The jump from chemistry to biology is not inevitable. It requires not just the right ingredients, but the right circumstances, the right sequence of events, perhaps even the right luck. But the possibility is there, written in stone, preserved in the geological record. Early Mars was habitable, not in some abstract theoretical sense, but genuinely, physically habitable. A place where, if you could somehow have stood on its surface wearing the right equipment, you would have looked out over landscapes that felt familiar, water flowing, clouds moving, an environment dynamic and active and, in its own way, welcoming. This is the first world we're speaking of when we ask if Mars may have been inhabited twice. The cradle, the ancient paradise, the Mars that could have been. But here's the thing about cradles and paradises. They're fragile. They depend on systems remaining in balance, on shields holding firm, on cores staying hot and dynamos continuing to spin. And on Mars, something went wrong. We don't know exactly when. Probably somewhere between 4 billion and 3.5 billion years ago, though the precise timing is still debated. It might have been sudden, geologically speaking, or it might have been gradual, a slow fade taking millions of years. But at some point, the magnetic field began to weaken. Perhaps the core cooled too quickly, Mars being smaller than Earth and losing its internal heat faster. Perhaps a catastrophic impact disrupted the convection currents that drove the dynamo. Perhaps it was simply inevitable, written into the planet's fate by its size and distance from the sun. Whatever the cause, the shield began to fail, and once it did, the solar wind had its way. Year by year, century by century, millennium by millennium, the atmosphere thinned. The pressure dropped, the warmth bled away into space. The rivers slowed to trickles, then froze, then ceased to flow at all. The lakes evaporated or turned to ice. The clouds dissipated. The rain stopped falling. Mars entered a long, slow winter from which it has never emerged. The valleys we see today carved by water stand as monuments to what was lost. They are not features of the current Mars. They are scars from the past, testaments to forces that shaped a world and then abandoned it. How long did the first world last? That's the question that keeps scientists up at night, because the answer matters profoundly to the question of life. If the wet epoch lasted only a few tens of millions of years, then life would have had a narrow window to arise, to establish itself, to spread. Possible, but difficult. But if it lasted longer, 100 million years, 200 million years, perhaps even more, then life would have had time. Time to emerge, time to evolve, time to adapt to changing conditions as the planet slowly dried and cooled. The geological record suggests the transition wasn't instantaneous. There are features from different epochs, evidence that water persisted in some places, even as it vanished from others. Perhaps there were refuges, regions where conditions remained favorable, even as the global climate deteriorated. Perhaps life, if it arose, found ways to hold on. But whether it lasted 100 million years or 500 million years, whether life arose or remained forever on the cusp of possibility, one thing is certain. The first world ended, not with a bang, not with the dramatic finality of a collision or explosion, but with a whimper, a slow fading, an erosion of everything that had made Mars a place where water could flow, and air could shelter, and warmth could linger. By 3 billion years ago, the Mars we know today had largely taken shape, cold, dry, thin-aired, a planet wrapped in silence, and it has remained that way ever since. For 3 billion years, Mars has been a frozen desert, its surface sculpted only by wind and the occasional impact, its water locked away as ice at the poles or buried beneath the surface, its atmosphere so tenuous that it barely deserves the name. 3 billion years is a long time. Long enough for continents to drift on Earth, long enough for life to evolve from single cells to the vast complexity of the modern biosphere, long enough for nearly everything that defines our planet's surface to be shaped and reshaped dozens of times over. And through all of that time, Mars remained unchanged, locked in stasis, a world that had aged into stillness. But here's where our story takes an unexpected turn. Because the planet we see today, frozen and ancient and seemingly eternal in its desolation, may not be telling us the whole truth. There are hints in the geology, anomalies in the timeline, features that seem too young, too fresh, too out of place in a world that supposedly died 3 billion years ago. What if the first world wasn't the only chapter in Mars's story? What if, long after the rivers stopped flowing and the lakes turned to ice, something happened that gave Mars a second chance? Paradise is fragile, and on Mars, it ended abruptly. But perhaps, just perhaps, it returned. There are many ways for a world to die. Some end in fire, consumed by their parent star as it swells into a red giant, engulfing everything that once orbited safely beyond its reach. Others are shattered by collision, broken apart in cosmic accidents that reduce planets to rubble and dust. Some freeze slowly as their sun dims and cools, the warmth that sustained them fading over billions of years until nothing remains but ice and darkness. But Mars died differently. Mars died by degrees, by erosion, by a slow unraveling of the very systems that had kept it alive. It was a death that took millions of years to complete, and yet, in geological terms, it happened quickly, catastrophically. A planetary tragedy playing out in slow motion across the ancient solar system, witnessed by no one, recorded only in the stones themselves. The beginning of the end was invisible, deep beneath the Martian surface, in the churning metallic core that had once generated the planet's protective magnetic field. Something fundamental changed. The currents began to slow. Mars is smaller than Earth, only about half our planet's diameter, with barely a tenth of Earth's mass. And size, in planetary physics, is destiny. A smaller world has less volume relative to its surface area. It radiates heat more efficiently. Its interior cools faster. For perhaps 500 million years, maybe longer, Mars's core had remained hot enough to stay molten, liquid iron stirring in convective patterns that generated electrical currents, transforming the planet's interior into a dynamo, a generator of magnetism on a planetary scale. But as the eons passed, heat bled away into space. The temperature dropped, the convection weakened, and at some point, perhaps 4 billion years ago, perhaps slightly earlier or later, the dynamo sputtered and failed. The magnetic field began to collapse. This wasn't like flipping a switch. The field probably fluctuated for a time, weakening and strengthening, perhaps even reversing its poles as Earth's field does periodically. But the trend was unmistakable. The shield was failing. And without that shield, Mars was exposed. The sun, our life-giving star, our source of light and warmth, is also a weapon. Every second it hurls 1 million tons of matter into space at speeds exceeding 1 million kilometers per hour. This is the solar wind, a plasma of charged particles, mostly protons and electrons, streaming outward from the sun's corona in all directions, filling the solar system with invisible radiation. On Earth, we barely notice it. Our magnetic field deflects it, channeling the charged particles around our planet, funneling them toward the poles where they interact with our upper atmosphere to create auroras, shimmering curtains of light that paint the night sky green and red and violet. The solar wind never reaches our lower atmosphere, never touches the air we breathe. Our magnetic cocoon keeps it at bay. But once Mars lost its field, it had no such protection. The solar wind hit the Martian atmosphere directly, and it began to tear it apart. The process is called atmospheric sputtering, and it's brutally efficient. High-energy particles from the sun collide with molecules in the upper atmosphere, carbon dioxide, nitrogen, water vapor. The collisions transfer energy. The molecules accelerate. Some of them accelerate beyond escape velocity, and they simply drift away into space. One molecule at a time, Mars bled its atmosphere into the void. NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, watches this process happening even now. With instruments designed to measure the escape of atmospheric gases, MAVEN has quantified the ongoing loss, about 100 grams per second, escaping constantly, a hemorrhage that never stops. 100 grams per second might not sound like much, but let that run for 1 million years, for 10 million years, for hundreds of millions of years. The numbers become staggering. Over geological time, Mars has lost the equivalent of an entire planetary atmosphere, perhaps several atmospheres worth. The thick protective blanket of air that once shielded the surface and trapped warmth and allowed water to flow, gone, molecule by molecule, stripped away by the relentless solar wind. And as the atmosphere thinned, everything else began to unravel. Atmospheric pressure dropped. Water that had been stable as a liquid began to boil away or freeze, no longer able to exist in its liquid state except under increasingly rare conditions. The greenhouse effect weakened. With less carbon dioxide in the air to trap infrared radiation, the surface temperature plummeted. The planet's average temperature dropped toward the brutal cold we see today, where even at the equator in summer, the warmth barely reaches above freezing. The rivers slowed. Their flow became intermittent, seasonal perhaps, dependent on brief periods of melting. And then they stopped flowing altogether. The lakes began to freeze. Ice formed at their surfaces, thickening with each passing winter that no longer gave way to warm summers. The deltas ceased their patient work of sediment deposition. The valleys, carved by running water, fell silent. Mars was transforming from a dynamic, active world into a frozen stillness. But the atmosphere didn't only escape into space. Some of it was lost through a different process, one that locked away the air itself inside the planet's crust. Carbon dioxide, the primary component of the early Martian atmosphere, is chemically reactive. In the presence of water and certain minerals, it undergoes a transformation called carbonation, combining with rocks to form carbonate minerals. On Earth, this process is part of our planet's long-term carbon cycle, but it operates slowly, balanced by volcanic activity that releases CO2 back into the atmosphere. On Mars, as volcanic activity waned and the atmosphere thinned, carbonation became a one-way street. Carbon dioxide dissolved in water, reacted with rocks, and was locked away as solid carbonate deposits. The air turned to stone, and still more carbon dioxide was lost to ice. As the temperature dropped, CO2 began to freeze out directly from the atmosphere, condensing at the poles as dry ice. Thick layers of frozen carbon dioxide that remain there to this day, mixed with water ice, a fossil memory of the atmosphere that once enveloped the entire planet. Between sputtering into space, freezing at the poles, and reacting with rocks to form carbonates, the Martian atmosphere underwent a catastrophic collapse, and it happened relatively quickly. The geological evidence suggests that by 3.5 billion years ago, maybe 3 billion years ago at the latest, the transformation was largely complete. Mars had gone from a world with rivers and lakes and a water cycle to a frozen desert where liquid water could exist only briefly, in thin films, under specific conditions that became rarer with each passing age. 3.5 billion years ago. Think about what that means. Life had already arisen on Earth by then. Our planet's oceans were full of microbial life, bacteria, and archaea that had been evolving for perhaps 500 million years already. And Mars, which may have been habitable at the same time, which may have had its own wet epoch overlapping with Earth's earliest biosphere, was dying, or perhaps already dead. But was it only the loss of the magnetic field and the slow escape of atmosphere that killed Mars? Or was there something more violent, more sudden, that accelerated the planet's decline? The answer may lie written in the largest scars on the Martian surface. Look at Mars from orbit, and you'll notice something strange about its topography. The planet is lopsided. The southern hemisphere is ancient, heavily cratered, sitting several kilometers higher in elevation than the northern plains. The northern hemisphere is younger, smoother, lower, as if something had scoured away the original surface and left a vast, relatively flat basin in its place. This dichotomy has puzzled scientists for decades. What could cause such a profound difference between one hemisphere and another? One theory suggests a cataclysmic impact, not just a large impact, but a truly enormous one. An object perhaps the size of Earth's moon, or larger, slamming into the northern hemisphere of Mars with unimaginable violence, excavating a basin that covers 40% of the planet's surface. The Borealis Basin, as this feature is sometimes called, would be the largest impact structure in the solar system if this theory is correct. A wound so vast it permanently reshaped the planet's geography. And an impact of that magnitude wouldn't just excavate rock. It would have immediate devastating consequences for any atmosphere the planet still possessed. The energy released would be staggering. The impact would vaporize enormous quantities of rock and ice, blasting debris into space. It would generate a shock wave that would ripple through the entire planet. It would trigger earthquakes, volcanic eruptions, maybe even temporarily remelt portions of the crust and mantle. And it would blow away a significant fraction of the atmosphere in a single catastrophic event. Not through slow sputtering, but through explosive stripping, the sheer force of the collision, launching atmospheric gases into space faster than gravity could hold them back. If such an impact occurred during the period when Mars was already losing its magnetic field and undergoing atmospheric escape, it could have been the final blow. The event that accelerated Mars's transformation from a dying world to a dead one. We're not certain this happened. The evidence for the giant impact hypothesis is suggestive but not conclusive. Mars's northern lowlands could have formed through other processes, plate tectonics perhaps, or massive volcanic resurfacing, though neither explanation fits the evidence as neatly as we'd like. But whether it was a single catastrophic impact, a series of smaller collisions, or simply the relentless grinding erosion of the solar wind over millions of years, the result was the same. Mars's atmosphere was lost. Its water was lost. Its warmth was lost. Everything that had made it habitable vanished into space or was locked away in ice and stone. This is what scientists sometimes call a great filter. The term comes from discussions about the Fermi paradox, the question of why we haven't encountered evidence of other intelligent civilizations despite the vast number of stars and planets in the galaxy. One possible answer is that there are filters, barriers that prevent life from arising or surviving or reaching technological sophistication. Mars encountered such a filter, a planetary-scale barrier that transformed a habitable world into an inhospitable one. And here's the sobering thought. If Mars couldn't escape this filter, if a planet that once had water and air and warmth could lose it all so completely, what does that say about the fragility of habitability itself? Earth has been fortunate. Our planet is large enough that its core remains molten even after 4.5 billion years. Our magnetic field is still strong, still deflecting the solar wind, still protecting our atmosphere from being stripped away. We orbit at just the right distance from the sun, in the narrow band where water can remain liquid. We have active plate tectonics that recycle carbon and regulate our climate over geological time. Change any of those factors, and Earth could have followed Mars into frozen silence. Perhaps it still will, billions of years from now, when our own core finally cools and our magnetic field fails. But for Mars, the unmaking came early. The planet had barely finished forming before it began to die. By 3 billion years ago, the first world was gone. The rivers and lakes existed only as fossils, preserved in the geology. The thick atmosphere was a memory written in isotope ratios and carbonate deposits. The warmth and the possibility it represented had faded into an endless winter. For 3 billion years, more than half the age of the solar system, Mars has remained locked in this frozen state. 3 billion years of silence, of stillness, of a surface shaped only by wind and the slow, patient work of time. And yet, the scars of this collapse, the geological record of Mars's transformation from a wet world to a dry one, carry information. Clues not just to what was lost, but to what the planet was like before the unmaking began. We can read these clues. We can study the minerals that formed in the presence of water. We can analyze the isotopes that tell us about the thickness of the ancient atmosphere. We can map the valley networks and delta deposits and lakebeds that speak to hydrological cycles that once operated at a planetary scale. And in doing so, we can reconstruct not just what Mars lost, but what it once had. The first world may be gone, but it's not forgotten. It's written into every ancient stone, every layered outcrop, every dry riverbed that cuts across the highlands. And here's the thing about those scars. They also tell us where to look. If life arose during Mars's wet epoch, if biology managed to take hold during that brief window when conditions were right, then that life would have faced a crisis as the planet dried and cooled. It would have had to adapt, to retreat to refuges, to places where water still existed, where conditions remained stable even as the surface became inhospitable. Or it would have had to perish, leaving behind only fossils, chemical signatures, hints of what once was. Either way, the scars of the great unmaking would mark the places where life's last stand occurred, the regions where habitability persisted longest, the final refuges of the first world, and those places, identified through careful study of Mars's ancient geology, become targets. Places to search for evidence of what the first world might have created before it ended. But the scars tell us something else too, something we're only beginning to understand. They tell us that Mars's story might not have ended with the great unmaking, because death is not always permanent, even for planets. Yet the scars of this collapse carry clues, not just to what was lost, but what may have endured. When the surface of a world becomes uninhabitable, life has two choices. It can die, or it can descend. On Mars, as the atmosphere thinned and the rivers froze and the surface temperatures plunged to levels where no liquid water could persist, any life that had managed to arise during the wet epoch would have faced an existential crisis. The comfortable, sun-warmed surface was no longer viable. The energy that once flowed freely from a thicker atmosphere and warmer climate was vanishing. The water that had defined entire ecosystems was either escaping into space, freezing into permanent ice, or retreating underground. For life clinging to the surface, this would have been a slow apocalypse, a steadily tightening noose of cold and dryness and thinning air. But beneath the surface, conditions were different. The deep subsurface of Mars didn't care that the atmosphere was gone. It didn't notice the solar wind stripping away the air molecule by molecule. The temperature down there, insulated by kilometers of rock, remained relatively stable, controlled not by the thin Martian atmosphere, but by heat rising from the interior. And most importantly, there was still water, not on the surface, exposed to vacuum and cold, but locked in the pores and fractures of the crust. Water that had percolated down from ancient lakes and rivers, seeping through cracks, filling aquifers, creating vast subsurface reservoirs that could persist long after the surface had turned to frozen desert. If life had arisen on early Mars, the deep subsurface would have been the obvious refuge, the place to retreat as the surface became hostile. The shelter where biology could potentially endure not just for years or centuries, but for geological ages, for billions of years. The question is whether such a thing is actually possible. Can life survive in permanent darkness, cut off from the sun, buried under kilometers of rock for 3 billion years? The answer, surprisingly, is that we don't have to speculate. We can look at Earth and see life doing exactly that. In 2008, scientists drilling deep into a gold mine in South Africa, nearly 3 kilometers below the surface, discovered something extraordinary, a bacterium living in complete isolation from the surface world, thriving in water that had been trapped in fractures in the rock for millions of years. They named it Desulforudis audax viator. The name comes from a Latin phrase in Jules Verne's Journey to the Center of the Earth. It means bold traveler who relies on self. And the name is fitting because this organism is one of the most independent forms of life ever discovered. It doesn't need sunlight, it doesn't need oxygen, it doesn't need organic nutrients from the surface. It lives on chemistry alone. The rocks surrounding it contain uranium and other radioactive elements. As these elements decay, they produce radiation that splits water molecules into hydrogen and oxygen. Desulforudis uses that hydrogen as fuel, combining it with sulfate minerals dissolved in the water to generate energy. It builds all its own organic molecules from scratch, starting with carbon dioxide and inorganic compounds. It's a completely self-contained ecosystem of one, a single species living in the deep subsurface, extracting everything it needs from the rock and water around it, independent of the sun, independent of photosynthesis, independent of the entire biosphere flourishing kilometers above. And it's not alone. Deep subsurface ecosystems have been found all over Earth, in aquifers beneath continents, in fractures in oceanic crust, in mines and boreholes from South Africa to Canada to Scandinavia. Anywhere we drill deep enough and look carefully enough, we find life. Not just bacteria, entire communities. Archaea, fungi, even tiny multicellular organisms called nematodes. Living at depths where sunlight has never reached, where the temperature approaches the boiling point of water, where the pressure is crushing, and the chemistry would be lethal to surface organisms. These deep biospheres, as they're called, represent a massive amount of living biomass. Some estimates suggest that the total mass of microorganisms living in Earth's deep subsurface rivals, or exceeds the mass of all life on the surface. We live on the skin of the Earth, but the Earth's flesh, kilometers deep, is alive too. And if this is true on Earth, why not Mars? Mars has a fractured crust. The same impacts that cratered its surface also created networks of cracks extending deep into the lithosphere. Water that once flowed on the surface would have percolated down through these fractures, creating aquifers at depth. Mars has heat sources. Its core may have cooled enough to shut down the global magnetic field, but pockets of warmth would have persisted for a long time. Radioactive decay in the crust generates heat continuously. Localized volcanic activity, hot springs, hydrothermal systems, all of these could have provided the energy needed to keep subsurface water liquid long after the surface froze. Mars has chemistry. The rocks contain sulfates, iron minerals, hydrogen, the same basic ingredients that Desulforudis uses on Earth, the same resources that deep subsurface life exploits in terrestrial environments. In other words, Mars has, or had, the prerequisites for a deep biosphere. If life arose during the wet epoch, it would have had millions of years to diversify, to explore different ecological niches, to adapt to different environments. And some of those niches would have been in the subsurface, in hydrothermal systems fed by volcanic heat, in aquifers filled with mineral-rich water. When the surface became uninhabitable, those subsurface communities wouldn't necessarily have died. They were already living independently of the surface, already adapted to darkness and chemistry and stable, unchanging conditions. They might have simply continued, oblivious to the catastrophe happening above. Imagine what that would mean. Life arising during the Noachian epoch, 4 billion years ago, spreading through the surface waters, yes, but also colonizing the subsurface, evolving in darkness, learning to live on chemical energy alone. And then the great unmaking begins. The atmosphere escapes, the surface freezes, Everything exposed to the Martian sky dies or goes dormant, locked in ice. But beneath the surface, nothing changes. The water is still there, still liquid. The heat is still there, rising from below. The chemistry is still there, providing energy. Life in the deep refugia continues for 100 million years, 1 billion years, 3 billion years. While the surface of Mars remains frozen and sterile, the subsurface could harbor a living biosphere, small perhaps, limited, but persistent, waiting in the dark. Of course, survival for 3 billion years in isolation is an extraordinary claim. And extraordinary claims require extraordinary evidence, which we don't yet have. But the possibility is not as far-fetched as it might seem. Deep subsurface life on Earth lives slowly. Metabolism is reduced to a crawl. Cell division might occur once every 100 years, or once every 1,000 years. Time in these environments operates on a completely different scale than on the surface. Evolution slows down proportionally. A lineage that might accumulate significant changes in 10,000 years on the surface might remain virtually unchanged for millions of years in the deep subsurface. Stasis becomes possible. Long-term stasis, where organisms persist in a kind of geological suspended animation, barely alive by surface standards, but stable, enduring, maintaining the basic machinery of life across unimaginable stretches of time. And there's another possibility, even more remarkable: dormancy. Some bacteria on Earth can form spores, protective capsules that shut down all metabolism, all activity, entering a state of suspended animation that can last for centuries, perhaps longer. The oldest confirmed revival of bacterial spores is around 250 million years from salt crystals in New Mexico. Whether spores can remain viable for billions of years is unknown. The theoretical limits aren't clear. DNA degrades over time, damaged by background radiation and chemical decay. But under the right conditions, cool and dry and shielded from radiation, protected inside rock or ice, dormancy might be possible for extraordinary durations. Imagine Martian life retreating into ice as the surface froze, not dying, but entering dormancy, waiting, for 3 billion years. It sounds like science fiction, but we simply don't know the limits. We haven't tested them. We haven't had time to test them. 3 billion years is a long time, longer than multicellular life has existed on Earth. Longer than oxygen has dominated our atmosphere, long enough for entire eons to pass, for continents to drift, for impact craters to form and erode away. And through all of that time, Martian life in the deep subsurface, if it existed, would have been evolving. Slowly, yes, but evolving nonetheless. Adapting to the unchanging darkness, refining its metabolism, becoming more efficient at extracting energy from chemistry, diversifying into whatever niches the subsurface provided, or perhaps not evolving at all, perhaps remaining essentially unchanged, locked in a stable equilibrium with its environment, a living fossil from the Noachian epoch. Either way, if life went underground when the surface died, it could still be there, right now, today, living in aquifers we haven't sampled, in fractures we haven't drilled into, in pockets of warmth surrounding volcanic intrusions we haven't detected, invisible, silent, unknown. A ghost biosphere haunting the depths of Mars while our rovers traverse a sterile surface above. This is not idle speculation. This is a legitimate scientific hypothesis based on what we know about life's tenacity on Earth and the conditions that exist in Mars's subsurface. And it has profound implications for how we search for life on Mars. If Martian life exists only in the deep subsurface, we'll never find it by studying surface rocks. The rovers can't drill deep enough. They scratch the upper few centimeters, occasionally boring a few inches into boulders. But the deep subsurface is kilometers down, beyond our reach with current technology. We need to find places where the subsurface has been exposed, where impacts have excavated deep craters, bringing up material from depth, where ancient hydrothermal systems have left mineral deposits on the surface, where erosion or tectonic activity has revealed what lies beneath. Or we need to wait for future missions that can drill deeper, missions designed specifically to access subsurface water, to sample aquifers, to search for biosignatures in environments that have remained stable while the surface transformed into desert. The search for Martian life has largely focused on the wet epoch, on trying to find evidence of life that existed 4 billion years ago when the surface was habitable. But if life went underground, the relevant question isn't whether it existed in the past, it's whether it still exists now. That's a very different question, one that changes the entire nature of the search. Because if there's an extant Martian biosphere, even a tiny one limited to the deep subsurface, then Mars isn't a dead world. It's a living one. A world with its own independent biology, its own evolutionary history, its own adaptations and survival strategies. And finding it would be one of the most profound discoveries in human history. But the subsurface refugia, if they exist, are not the whole story. Because Mars, despite losing its atmosphere and freezing solid and remaining locked in that frozen state for 3 billion years, was not finished changing. The planet had one more surprise in store, one more chapter in its long, strange history. Something that would transform the surface again. Something that might, just possibly, have given life a second chance. Not in the deep, silent refugia where chemistry alone sustains existence, but on the surface, in the light, in environments that resembled, however briefly, the paradise that had been lost 3 billion years before. But Mars was not done stirring. For 3 billion years, Mars slept. The surface remained frozen. The atmosphere stayed thin. The rivers that had carved those ancient valleys never flowed again. The planet had settled into what seemed like a permanent equilibrium, a cold, dry stasis from which there appeared to be no escape. But planets, like all things in the universe, are not truly static. They change, they evolve, sometimes imperceptibly slowly, sometimes in sudden bursts of activity that transform everything. And Mars, despite its long sleep, was not quite finished with transformation. Because deep beneath that frozen surface, despite the cooling of the core and the loss of the global magnetic field, there were still pockets of heat, regions where molten rock persisted, places where the planet's interior remained active, churning, waiting for the right conditions to express itself. And, eventually, it did. Look at the Tharsis region, a vast volcanic plateau that dominates the western hemisphere of Mars, crowned by some of the largest volcanoes in the solar system. Olympus Mons, rising 25 kilometers above the surrounding plain, 3 times the height of Mount Everest. Arzia Mons, Pavonis Mons, Ascraeus Mons, a chain of massive shield volcanoes that together cover an area larger than the continental United States. These volcanoes are ancient. Their bases date back billions of years. But here's the remarkable thing. They're not as old as the Great Unmaking, or rather, they didn't stop erupting when the first world died. Crater counting, the technique we use to date Martian surfaces, suggests that some flows on these volcanoes are relatively young, perhaps a few 100 million years old. Some estimates push certain features to even more recent times. Tens of millions of years, maybe even a few million years ago. In geological terms, that's yesterday. The same is true for the Elysium region, a smaller volcanic complex on the opposite side of the planet. Flows there show similarly young ages, evidence of volcanic activity that occurred long after Mars was supposed to have gone geologically quiet. These weren't the massive, sustained eruptions that built the volcanoes in the first place. These were episodic pulses, intermittent activity. But they happened nonetheless, And when a volcano erupts, it doesn't just release lava, it releases gases, volatiles that have been trapped in the molten rock, dissolved under pressure, suddenly freed when the magma reaches the surface. Water vapor, carbon dioxide, sulfur compounds, everything that once made up the Martian atmosphere. A single large eruption wouldn't change the planet's climate. The thin atmosphere and low pressure would mean that any released gases would quickly escape or freeze out. But what about a sustained period of eruptions? A volcanic pulse lasting thousands of years, or tens of thousands of years, pumping greenhouse gases into the atmosphere continuously. The model suggests something remarkable. Under those conditions, the Martian atmosphere could temporarily thicken. Pressure at the surface could rise. Temperatures could increase, if only slightly, and liquid water could briefly flow again. Not everywhere, not in the stable, long-lasting way it did during the Noachian epoch, but in localized regions near the volcanoes themselves, where heat and outgassed water vapor combine to create transient hydrothermal systems. Where snowmelt during brief warming periods could form seasonal streams. Windows of habitability, brief, unstable, but present. A second dawn, not as glorious as the first, not as long-lasting, not as warm, but a dawn nonetheless. This idea that Mars might have experienced intermittent periods of surface habitability long after the wet epoch ended is relatively new. It emerged from careful study of the planet's volcanic history, from improved dating techniques, from climate models that can simulate what happens when you pulse the Martian atmosphere with volcanic gases. And it raises a profound question. If conditions on the surface temporarily improved, if liquid water became available again even briefly, could life have taken advantage? There are two possibilities, and both are staggering in their implications. The first possibility is re-emergence. If life had retreated to the subsurface when the first world ended, if it had been surviving in deep aquifers and hydrothermal systems for billions of years, then episodic volcanic activity would represent an opportunity. Because volcanic systems connect the surface to the deep subsurface, magma rises from depth, heating groundwater, creating circulation. Water from subsurface aquifers can be drawn up toward regions of volcanic warmth, emerging at the surface as hot springs, as geysers, as hydrothermal vents. On Earth, these volcanic hydrothermal systems are hotspots of biological activity. Life thrives wherever hot water meets cold, wherever chemical gradients form, wherever energy flows from the planet's interior to the surface. If Martian life existed in the subsurface, volcanic episodes would give it a pathway to the surface, a route up from the dark refugia into environments that, however briefly, resembled the world that existed before the Great Unmaking. And once on the surface, if conditions remain favorable for even a few thousand years, life could potentially spread. Not far, perhaps, not globally, but locally around volcanic centers, in whatever pockets of warmth and moisture existed. A bloom, a flourishing, a temporary renaissance. And then, when the volcanic activity ceased and the atmosphere thinned again and the cold returned, life would retreat once more into the subsurface. Back to the refugia. Back to the slow, patient existence in darkness, only to emerge again the next time Mars stirred, the next time a volcanic pulse warmed the surface. Cycles of emergence and retreat, playing out over billions of years, life flickering on the Martian surface like a candle that keeps reigniting, burning briefly, then guttering out, only to spark again when conditions allow. That's one possibility. The second possibility is even more extraordinary. Reawakening. If life had gone dormant during the Great Unmaking, if it had locked itself in ice or buried itself in surface sediments, entering a state of suspended animation, then warming events would represent a chance to revive. Imagine microbial spores, frozen for 3 billion years in ancient ice deposits. Then a volcanic episode warms the region. The ice melts. Water flows, however briefly. The spores are exposed to liquid water again, to warmth, to the basic conditions necessary for metabolism. And they wake up. It sounds fantastical, but we know that extremophiles on Earth can survive freezing for extended periods. We've revived microbes from permafrost that's been frozen for hundreds of thousands of years. We've found viable bacteria in ice cores dating back nearly 1 million years. 3 billion years is a completely different scale. We don't know if dormancy can last that long. The limits haven't been established. But the theoretical possibility exists. And if it's possible, then every warming event on Mars over the past 3 billion years would have been a potential trigger for revival, a chance for ancient Martian life to reanimate, to briefly metabolize and reproduce, before freezing again when the warmth departed. Whether through re-emergence from the subsurface or reawakening from dormancy, the implications are profound. It means that Mars might not just have been inhabited once during the Noachian epoch. It might have been inhabited repeatedly, multiple times, across billions of years. Brief episodes of life separated by vast stretches of sterile cold. And here's the thing, we have hints that something like this might actually have happened. Starting in 2011, the Mars Reconnaissance Orbiter began detecting something strange on certain steep slopes in the southern hemisphere. During the Martian summer, dark streaks would appear, flowing downslope, finger-like features that elongated over the course of weeks or months. Then, as winter returned, they would fade. The next summer, they would reappear in the same locations. Recurring slope lineae, or RSL. Scientists have been arguing about them ever since. The initial interpretation was tantalizing. These features looked like they could be caused by flowing water. Briny water, salty enough to remain liquid at Martian temperatures, seeping from subsurface sources, running downslope, then evaporating or soaking back into the ground. Seasonal liquid water. On Mars. Today. If true, it would mean that Mars still has active hydrological processes. That liquid water still exists, however briefly, on the modern surface. The implications for habitability are obvious. If there's liquid water, there's the potential for biology, not complex life certainly, but microbial life. Extremophiles adapted to high salinity and low temperatures could potentially exploit these transient flows. But the interpretation has become more complicated. Further studies suggested that some RSL might be caused by dry granular flows, avalanches of sand triggered by seasonal temperature changes without any water involvement at all. The debate continues. Some RSL features still appear to require liquid water to explain, others probably don't. The truth is likely that RSL are diverse phenomena, some involving water, some not. But the very fact that we're having this conversation, that we're seriously considering the possibility of seasonal liquid water on modern Mars, tells you how much our understanding has evolved. Mars is not as dead as it appears, and there's another factor that might periodically revive surface conditions, one that has nothing to do with volcanoes or subsurface water. Orbital mechanics. Mars's axial tilt, the angle at which it's tilted relative to its orbital plane, is not stable the way Earth's is. Our moon acts as a stabilizer, keeping Earth's tilt locked at about 23.5 degrees, barely varying over millions of years. Mars has no large moon, nothing to stabilize it, and as a result, its axial tilt wanders wildly over geological time. Currently, Mars is tilted at about 25 degrees, similar to Earth, but calculations show that over cycles lasting hundreds of thousands to millions of years, that tilt can swing dramatically, from as low as 10 degrees to as high as 60 degrees or more, and axial tilt controls climate. When Mars's tilt is low, the poles receive less direct sunlight. They get colder. More ice accumulates there, thickening the polar caps, locking away carbon dioxide and water. When the tilt is high, the poles receive more summer sunlight. they warm. Ice sublimates. Water vapor and carbon dioxide are released into the atmosphere. At extreme tilts, the poles can become warmer than the equator during summer. Ice deposited at the poles during low-tilt epochs would sublimate rapidly, potentially thickening the atmosphere by a measurable amount. And a thicker atmosphere means higher surface pressure, which means the possibility of liquid water, at least seasonally, in certain locations. Models suggest that during high obliquity epochs, Mars could experience conditions significantly more hospitable than today. Not as warm or wet as the Noachian, nowhere close, but warmer and wetter than the frozen desert we currently observe. Enough perhaps for transient surface water, for seasonal flows, for environments where microbial life, if it existed in the subsurface, could briefly exploit surface conditions. These high obliquity epochs occur cyclically, every few 100,000 years, perhaps more frequently, and they've been happening for billions of years, each one a potential window, a potential second dawn, or third dawn, or thousandth dawn. Brief moments when Mars, despite its thin atmosphere and frozen surface, offers just enough warmth and water for life to make a temporary appearance. The picture that emerges is radically different from the simple narrative of a planet that died 3 billion years ago and has remained dead ever since. Instead, we're looking at a planet that might experience episodic habitability. Long periods of sterile cold punctuated by brief windows, thousands of years, maybe tens of thousands of years, when conditions improve enough to allow liquid water and, potentially, biological activity. It's a strange kind of habitability, intermittent, unstable, fleeting. But it's habitability nonetheless. And if life found a way to exploit these windows, if it learned to survive the long freezes between warming episodes, then Mars might host a biosphere unlike anything we've imagined. Not a continuous stable biosphere like Earth's, but a flickering one, a pulse. Life that appears and disappears with the cycles of the planet, tied to volcanic activity and orbital variations and whatever other factors temporarily warm the surface. A boom and bust ecology operating on geological timescales. We have no direct evidence that this has happened, no confirmed detection of extant Martian life, no biosignatures in the recurring slope lineae, no unambiguous signs of biology in any of the samples our rovers have analyzed. But the absence of evidence is not evidence of absence, especially when we've barely scratched the surface. And the theoretical possibility is there, written into the planet's recent geological history, suggested by young volcanic flows and orbital mechanics and features that at least might involve liquid water. Mars may have offered life a second chance, or a third chance, or many chances, spread across billions of years. And if those chances were taken, if life did re-emerge or reawaken during warming episodes, then somewhere on Mars, perhaps in ice, perhaps in sheltered deposits near volcanic centers, there might be evidence. Fossils from the second world, or the third, or the thousandth. Chemical signatures of biological activity that occurred not 4 billion years ago, but recently, geologically recently, maybe even within the last million years. That's the explosive implication of the second dawn hypothesis. It transforms Mars from a dead world that we study for ancient history into a potentially living world that we need to investigate for current biology. It changes everything about how we search and where we search and what we expect to find. But it also raises questions that we're only beginning to grapple with. Questions that strike at the heart of what we think we know about life and planets and habitability. And then, the hardest question of all surfaced from the thin Martian air. There is something in the Martian air that shouldn't be there, something subtle, measured in parts per billion, so faint that for years scientists debated whether it existed at all or was merely instrumental noise, a phantom signal hiding in the data. But it's real, and it behaves in a way that is profoundly unsettling. It rises, it falls, it appears with the seasons and fades again, following a rhythm that feels disturbingly organic, almost like breathing. The molecule is methane, 4 hydrogen atoms bonded to a single carbon atom, simple, common throughout the solar system. On Earth, it's produced by volcanoes, by geological processes, by the decay of organic matter in wetlands, and by life, specifically by microorganisms called methanogens, archaea that live in oxygen-free environments, in swamps and deep ocean sediments and the guts of animals, producing methane as a metabolic byproduct. On Earth, the vast majority of atmospheric methane comes from biological sources. So, when scientists detected methane in the Martian atmosphere, the question was immediate and obvious. Where is it coming from? The first detections came in 2003 from Earth-based telescopes and the Mars Express orbiter, faint signatures suggesting methane concentrations in certain regions, particularly above areas like Syrtis Major and Neely Fossé. The findings were controversial. Methane shouldn't persist in the Martian atmosphere for long. UV radiation from the sun breaks it down relatively quickly, on timescales of a few hundred years. For methane to be detectable, something has to be producing it continuously, replenishing it faster than it's destroyed. Something active, something ongoing. But the early detections were at the edge of instrumental sensitivity. Skeptics questioned whether the signal was real or an artifact of the observation technique. The debate simmered for years without resolution. Then Curiosity landed in Gale Crater in 2012, and it carried an instrument specifically designed to sample the Martian atmosphere and analyze its composition with extraordinary precision. The tunable laser spectrometer, part of the sample analysis at Mars suite, capable of detecting methane at concentrations as low as a few parts per billion. Curiosity began taking regular measurements, and what it found was strange. Most of the time, the methane concentration in Gale Crater was very low, background levels barely detectable. The atmosphere appeared essentially free of methane, but then, episodically, the concentration would spike, not by a little, by a lot. 10 times the background level, sometimes more. Pulses of methane appearing in the local atmosphere, persisting for weeks, then fading back to background levels, and the spikes showed a pattern. They occurred preferentially in late summer and early fall in the Martian northern hemisphere. During winter, methane levels dropped to nearly zero. Come summer again, the concentrations would rise, a seasonal cycle, repeatable, consistent across multiple Martian years. The data was unambiguous. Something in or near Gale Crater was releasing methane into the atmosphere seasonally, a source that activated during warmer months and went quiet during colder ones. The implications were staggering, because while geological processes can produce methane, they don't typically turn on and off with the seasons. Volcanoes don't erupt on seasonal schedules. Chemical reactions in rocks don't care what month it is, but biology does. On Earth, microbial activity is strongly temperature dependent. When it's warm, microbes metabolize faster, reproduce more quickly, consume more resources, and produce more waste gases. When it's cold, they slow down or go dormant. If methanogenic microbes existed in the Martian subsurface, accessing seasonal variations in temperature or water availability, they might produce methane pulses that correlate with summer warming. Exactly the pattern Curiosity was seeing. Of course, correlation is not causation. The seasonal pattern doesn't prove biology, but it's consistent with biology. And that alone is enough to make this one of the most important scientific mysteries currently facing planetary science. Could we be detecting the metabolic output of an extant Martian biosphere? But here's where the mystery deepens into paradox. While Curiosity was detecting these seasonal methane pulses from the surface of Gale Crater, there was another spacecraft studying Mars's atmosphere from orbit. The European Space Agency's Trace Gas Orbiter, or TGO, launched specifically to map the distribution of trace gases in the Martian atmosphere with unprecedented sensitivity. TGO arrived at Mars in 2016 and began science operations in 2018. Its instruments were designed to detect methane at concentrations as low as 50 parts per trillion, an order of magnitude more sensitive than previous orbital observations. Scientists expected TGO to map the methane plumes, to identify where they were coming from, to trace them back to their sources, and finally, resolve the question of what was producing this enigmatic gas. Instead, TGO found almost nothing. In its global surveys of the Martian atmosphere, TGO has detected essentially no methane, upper limits so low that the earlier orbital detections from 2003 appear to have been spurious. The Mars Express signals that started this entire investigation may have been instrumental artifacts after all. From orbit, Mars appears to have no significant atmospheric methane, and yet Curiosity, sitting on the surface, continues to measure it. The seasonal spikes persist in the data, regular as clockwork, undeniable. How can this be? How can methane be present at the surface but invisible from orbit? This is the methane paradox, and it's driven some scientists to question whether we really understand Martian atmospheric chemistry as well as we thought. One possibility is that the methane is extremely localized, released from point sources in such small quantities that it disperses before reaching altitudes where TGO can detect it. Curiosity happens to be sitting near one of these sources, measuring the gas in its immediate vicinity, while the global atmosphere remains methane-free. This would require very efficient mixing and destruction of the methane, some unknown process that breaks down the molecules faster than models predict, preventing them from accumulating in the global atmosphere. Or perhaps the methane is released at night, or during seasons when TGO isn't looking in the right places at the right times. Orbital observations are snapshots, not continuous monitoring. If the methane pulses are brief and highly variable, TGO might simply be missing them. But these explanations feel unsatisfying. They require special circumstances, fine-tuned conditions, a kind of cosmic conspiracy to make the observations fit. The simpler explanation, that one set of observations is wrong, seems more likely. Either Curiosity's detections are artifacts, or TGO's non-detections are incomplete. But Curiosity's instrument has been checked and rechecked. The measurements have been validated. And the seasonal pattern argues against random error. So, we're left with a mystery, a genuine scientific puzzle that multiple missions and multiple instruments have failed to resolve. And at the heart of that puzzle is the question of what's producing the methane in the first place. There are three main candidates. The first is geological, specifically a process called serpentinization. When water interacts with certain iron-rich minerals like olivine, common in Martian rocks, a chemical reaction occurs that produces hydrogen gas. That hydrogen can then react with carbon compounds to form methane. This process occurs on Earth in hydrothermal systems, particularly in mid-ocean ridges where seawater circulates through hot, freshly exposed mantle rocks. It's completely abiotic, requiring no biology whatsoever, and it could happen on Mars, anywhere that subsurface water comes into contact with the right minerals and sufficient heat. Ancient hydrothermal systems, regions of recent volcanic activity, deep aquifers where chemical reactions proceed slowly over geological time. Serpentinization is appealing because it explains methane production without invoking life. But it doesn't easily explain the seasonal variability. Why would serpentinization suddenly increase in summer and decrease in winter, unless the water supply is seasonal, unless aquifers near the surface freeze in winter and thaw slightly in summer, allowing chemical reactions to proceed when liquid water is present and halting them when everything freezes solid? It's possible. But it requires Mars's subsurface to be more hydrologically active than we generally assume. The second candidate is stored methane released from ancient reservoirs. Methane can be trapped in molecular cages of ice called clathrates. These form when water freezes under pressure in the presence of methane, creating a solid compound that can store large quantities of gas in a relatively small volume. On Earth, methane clathrates exist in abundance beneath the ocean floor and in permafrost regions. They're stable at high pressure and low temperature. When those conditions change, when the ice warms or the pressure drops, the clathrates destabilize and release their trapped methane. If Mars had a wet epoch with abundant organic matter or geological methane production, clathrates could have formed in the subsurface, trapping methane that was produced billions of years ago. Those clathrates could still exist today, buried in permanently frozen ground. And during seasonal warming, when surface temperatures rise and heat penetrates slightly deeper into the subsurface, the clathrates at shallow depths could destabilize, releasing their ancient methane into the atmosphere. This would produce seasonal pulses without requiring any current biological or geological activity. The methane would be fossil gas, a remnant from the ancient past, slowly leaking out whenever conditions allow. It's an elegant explanation, but it also requires that clathrates exist in significant quantities near enough to the surface to be affected by seasonal temperature changes. We have no direct evidence that they do. And then there's the third candidate, life. Methanogenic microbes living in the Martian subsurface, producing methane as a metabolic waste product. On Earth, methanogens are among the most ancient forms of life. They don't need oxygen, they don't need sunlight. They live in anaerobic environments, in deep sediments, in hydrothermal vents, in the guts of termites and cows and humans. They consume simple compounds, hydrogen, carbon dioxide, acetate, and produce methane. They're extremophiles. They thrive in conditions that would kill most other organisms. High salinity, low temperature, high pressure, complete darkness. The kinds of conditions that might exist in the Martian subsurface. If life arose on Mars during the wet epoch and retreated underground, when the surface became uninhabitable, methanogens would be among the most likely survivors. They require minimal resources. They're metabolically flexible. They can persist in environments where almost nothing else can. And if they exist, if they're active in subsurface aquifers or hydrothermal systems, they would produce methane continuously. The seasonal variation could come from temperature-dependent metabolism. Warmer summers would increase activity, boosting methane production. Cold winters would slow everything down, reducing output. Or the variation could come from seasonal changes in water availability. If shallow aquifers partially thaw in summer, providing liquid water for metabolic reactions, methane production would increase. In winter, when everything freezes solid, production would halt. From a biological standpoint, the seasonal methane pulses make perfect sense, but extraordinary claims require extraordinary evidence. And detecting methane, even with a seasonal pattern, is not extraordinary evidence. It's tantalizing, it's suggestive, but it's not proof. To prove biology, we'd need to detect other biosignatures, organic molecules with specific chirality, isotopic ratios that indicate biological fractionation, spatial patterns of methane concentration that correlate with features likely to harbor life. We'd need to rule out the geological explanations definitively, to show that serpentinization and clathrate release can't account for what we're seeing. And, ideally, we'd need direct detection, a sample from the subsurface that contains living cells, or unambiguous chemical evidence of metabolism. We don't have any of that yet. What we have is a mystery, a signal that appears and disappears with the seasons, a trace gas that shouldn't be there, produced by something we can't identify, through processes we don't fully understand. It could be geology. It could be ancient gas trapped in ice. It could be chemistry we haven't considered. Or it could be life, somewhere beneath the frozen surface of Mars, in aquifers or fractures or pockets of warmth surrounding dormant volcanic systems. There might be organisms, simple, ancient, adapted to extreme conditions, living slowly, metabolizing quietly, producing methane that seeps upward through the regolith and emerges into the thin atmosphere above, invisible, unreachable, but present, breathing. That's what the methane pattern feels like, a breath, an exhalation. Mars inhaling deeply during winter, holding still, then exhaling methane into the summer air. It's an unsettling metaphor, because breath implies life. And if Mars is breathing, what does that mean for everything we thought we knew about the planet? The scientific community remains divided. Some researchers are convinced the methane is geological, that we're seeing the last gasps of ancient chemical processes playing out in the subsurface. Others think clathrate release is the most likely explanation, fossil gas from 1 billion years ago finding its way to the surface. And some, cautiously, hesitantly, suggest that we should take the biological hypothesis seriously, that the pattern is too regular, too consistent, too much like what we'd expect from seasonal microbial activity to dismiss out of hand. The truth is, we don't know. We won't know until we can sample the subsurface directly, until we can drill into aquifers or excavate hydrothermal deposits or somehow access the regions where the methane is being produced. Future missions are being planned with exactly that goal in mind. Drills that can penetrate meters into the subsurface, instruments that can detect cellular structures or metabolic byproducts, strategies for accessing ice and analyzing it for trapped gases and organic compounds. But those missions are years away, perhaps decades. In the meantime, the methane continues its seasonal dance, rising and falling, present and absent, a ghostly signal from a world that may or may not be alive. And while that mystery remains unsolved, tantalizing us with the possibility of current life, other scientists are pursuing a different line of investigation. If the methane represents present life, that's extraordinary. But even if it doesn't, even if the gas turns out to be entirely geological, there's another search underway. A search not for the breath of living organisms, but for the remains of those that died billions of years ago. The fossils of the first world, preserved in stone, waiting to tell us whether Mars was ever truly inhabited. As scientists search for the fingerprints of present life, others look even deeper to the fossils of the first. Sometimes the most profound discoveries come not from distant spacecraft or robotic rovers, but from rocks that fall from the sky. In December of 1984, a geologist named Roberta Score was searching for meteorites in the Allen Hills region of Antarctica. It's one of the best places on Earth to find space rocks. The ice sheet acts as a conveyor belt, concentrating meteorites that have fallen over thousands of years into relatively small areas where they're exposed at the surface, dark against the endless white. She found a small rock, unremarkable at first glance, about the size of a potato, weighing less than 2 kilograms. Gray-green in color, angular, weathered, she cataloged it as ALH 84001 and sent it back with the rest of that season's collection. For nearly a decade, it sat in storage, just another meteorite among thousands, until someone thought to look at it more carefully and realized what it was: a piece of Mars. We know this from the gases trapped inside the rock, tiny bubbles of ancient Martian atmosphere, sealed in pockets within the meteorite, match the composition that Viking measured when it analyzed the air at the surface in 1976. The isotopic signature is unmistakable. This rock formed on Mars, was blasted into space by an asteroid impact, wandered the solar system for millions of years, and finally fell to Earth in Antarctica roughly 13,000 years ago. But here's what makes ALH 84001 extraordinary. The rock itself is ancient. Radiometric dating shows it crystallized from molten magma 4 billion years ago, during the Noachian epoch, during the wet era when rivers carved valleys and lakes filled with sediment. This stone remembers the first world, and in 1996, a team of scientists led by David McKay at NASA's Johnson Space Center announced that they'd found something inside it, structures, tiny, elongated, worm-like features, visible only under high-powered electron microscopes, ranging from tens to hundreds of nanometers in length. They looked like fossils. Specifically, they looked like fossilized bacteria. The announcement was explosive. President Clinton held a press conference. The discovery made headlines around the world. Here was physical evidence, something we could hold in our hands, that suggested Mars had once harbored life. But the scientific community was skeptical. Extraordinary claims require extraordinary evidence. And the evidence, while intriguing, was far from conclusive. The structures were small, smaller than most bacterial cells on Earth, though some terrestrial bacteria can be quite tiny under nutrient stress. Could they really be biological? They were found in carbonate minerals that had precipitated from water within fractures in the rock. The carbonates dated to around 3.9 billion years ago, formed when Mars still had liquid water. But carbonates can form through purely geological processes. Their presence didn't prove biology, and the structures themselves could potentially be explained as mineral formations. Magnetite crystals, iron sulfides, shapes created by chemical processes that happen to resemble biological forms without actually being biological. The debate has raged for nearly 30 years. Papers have been published arguing for and against the biological interpretation. New imaging techniques have been applied. The meteorite has been sliced and analyzed from every possible angle. And still, we don't have a definitive answer. Some scientists remain convinced that at least some of the structures in ALH 84001 are biosignatures, that the combination of the tiny features, the associated organic molecules, the specific types of mineral crystals, and their arrangement is best explained by biological activity. Others argue just as convincingly that every feature can be explained geologically, that we're seeing patterns in the noise, finding what we want to find because we want so desperately to discover that we're not alone. The truth is that proving ancient life from morphology alone is extraordinarily difficult. Fossilization is a process that degrades information. Even on Earth, where we have billions of examples of fossils and a complete understanding of the organisms that created them, scientists sometimes struggle to distinguish the oldest, bacterial fossils from mineral structures that formed abiotically. On Mars, where we have no context, no comparison, no living Martian biology to reference, the challenge is nearly impossible. ALH 84001 remains ambiguous, a tantalizing hint, a possibility, but not proof. Yet it represents something important beyond the specific question of whether those structures are fossils. It represents the idea that Mars can send us its stones, and within those stones might be written the answer to whether the planet was ever alive. Dozens of Martian meteorites have now been identified in collections around the world. Most are relatively young volcanics, basalts blasted off the surface by recent impacts, but some, like ALH 84001, are ancient. And if one ancient Martian rock happened to fall to Earth, there might be others. Rocks from the Noachian lakebeds, rocks from hydrothermal systems, rocks that formed in exactly the kinds of environments where life would have been most likely to arise and leave its mark. Finding them is a matter of chance, but the fact that they exist, that pieces of Mars naturally make their way to Earth, means we have a second pathway to search for ancient Martian life beyond sending missions to the planet itself. Though, of course, we're doing that too. And right now, in Jezero Crater, the Perseverance rover is engaged in one of the most important treasure hunts in the history of science. Perseverance landed in February 2021, touching down on the floor of a crater that 3.5 billion years ago was a lake. We can see the ancient delta where rivers once flowed in from the west, depositing sediment in fan-shaped formations that still stand as raised features on the crater floor. That delta is the target, Because if Mars had life during the Noachian, if microorganisms existed in the rivers and lakes, then the delta sediments are where we'd expect to find evidence. On Earth, river deltas preserve organic material. They bury it quickly under layers of sediment, protecting it from oxidation and decay. They create the kinds of fine-grained deposits where microscopic structures can be fossilized. They're natural archives of biological activity. If the same principles apply on Mars, the Jezero Delta is a library, and Perseverance is there to read it. The rover carries the most sophisticated suite of instruments ever sent to another planet. Cameras that can image features at microscopic scale, spectrometers that can identify minerals and organic compounds, a ground-penetrating radar that can map layers beneath the surface, and crucially, it carries a coring drill. As Perseverance explores the delta, it's collecting samples, drilling into carefully selected rocks, extracting cores about the size and shape of a stick of chalk, hermetically sealing them in ultra-clean titanium tubes, and caching them on the Martian surface. These are not just any rocks. Each target is chosen meticulously. Sedimentary layers that formed in water, carbonates that precipitated from ancient lakes, fine-grained mudstones where biosignatures, if they exist, would be most likely preserved. As of now, Perseverance has collected more than 20 samples, each one a time capsule from Mars's ancient past, each one potentially containing the answer to whether life arose on the planet. But here's the thing about those samples. We can't analyze them fully with the instruments on the rover. The technology is impressive, but it's limited by mass and power constraints. The cameras can't resolve cellular structures. The spectrometers can't definitively distinguish biological from geological organic compounds. To really know what's in those rocks, we need to bring them back to Earth. That's the plan. The Mars Sample Return Mission, a collaboration between NASA and the European Space Agency, is designed to retrieve the samples that Perseverance is collecting. A future lander will touch down in Jezero, deploy a small rocket, and launch the sample tubes into orbit around Mars. An orbiter will capture them and return them to Earth, where they'll be transferred to a secure facility for analysis with instruments that can't be miniaturized or sent to Mars. Mass spectrometers that can measure isotopic ratios to parts per trillion. Electron microscopes that can image at atomic resolution, techniques for detecting amino acids and their chirality, methods for identifying lipid biomarkers and molecular fossils. If there are biosignatures in those rocks, Earth-based laboratories will find them. The timeline is uncertain. Sample return missions are extraordinarily complex and expensive. Launch dates have slipped, budgets have ballooned. Some estimates suggest the samples might not return until the late 2030s, but they will return, eventually, and when they do, we'll have in our hands pieces of an ancient Martian lakebed, sediments that settled 3.5 billion years ago in water that flowed from highlands we can map, under skies that may have been full of clouds, the stones that remember, and they will either contain evidence of biology or they won't. There's no middle ground. Either Mars had life, and that life left traces we can detect, or it didn't. This is as close to a definitive answer as we're likely to get without drilling deep into the Martian subsurface or finding living organisms. But the samples from Jezero address only one part of the story. They tell us about the late Noachian, about the end of the wet epoch when the lakes were already starting to dry up and the climate was transitioning toward the frozen state we see today. They don't tell us about the earlier Noachian, about the period when Mars might have been at its most habitable, when the atmosphere was thickest and the climate was warmest and water was most abundant. For that, we need to understand something more fundamental about early Mars. We need to know whether the planet had an ocean. Look at the northern hemisphere of Mars from orbit. It's strikingly different from the south, lower in elevation by several kilometers, smoother, younger, less heavily cratered, and strangely flat. Vast plains that stretch for thousands of kilometers with remarkably little topographic variation. For decades, scientists have debated whether these northern lowlands were once filled with water, whether Mars, during its wettest period, had a northern ocean covering perhaps a third of the planet's surface. The idea is based on several lines of evidence. The flatness itself suggests leveling by water. The way ocean basins on Earth are smoothed by sediment deposition. There are features that resemble ancient shorelines, sinuous boundaries at specific elevations that trace across the landscape like tide lines. Deltas don't just exist in Jezero. There are dozens of valley networks across the southern highlands that appear to empty into the northern lowlands, as if rivers once drained from high ground into a low-lying sea. And the mineralogy is suggestive. Clay minerals, carbonates, sulfates, all indicators of water-rock interactions, are found in patterns consistent with a large standing body of water. But the evidence is far from definitive. The supposed shorelines are irregular, discontinuous, not at uniform elevations the way you'd expect from a static ocean surface. They could be the result of volcanic flows, or sediment deposits from wind, or any number of geological processes unrelated to water. The smoothness of the northern plains could be explained by volcanic resurfacing, ancient lava flows filling in the lowlands, creating the flat terrain we see today without any ocean required. And if there was an ocean, we need to explain where all that water went. Some would have been lost to space, some locked in ice. But an ocean's worth of water is a lot to lose, even over billions of years. The debate continues. Some researchers are convinced that early Mars had a northern ocean, at least episodically. Others think the evidence is too ambiguous, that we are interpreting features through the lens of what we want to find rather than what's actually there. But here's why it matters so much for the question of life. An ocean changes everything. If Mars had only isolated lakes and river systems, then habitable environments would have been limited. Life, if it arose, would have been restricted to those specific locations. Its diversity would have been constrained. Its chances of surviving the transition to a frozen world would have been lower. But if Mars had an ocean, even a cold one, even one that froze over seasonally, then it had a truly global hydrological system, water cycling from ocean to atmosphere to precipitation to rivers and back to the ocean. A planetary-scale environment where life could potentially spread and diversify. Oceans on Earth are the cradle of complexity. The places where life first arose and where it evolved into the stunning diversity we see today. If Mars had an ocean during the Noachian, even briefly, then the planet's biological potential was far greater than if it only had scattered lakes, and an ocean would have been a refuge. As the atmosphere thinned and surface conditions deteriorated, an ocean would have been the last place to freeze. The deepest water would have remained liquid longest, protected by the ice forming above, providing a final habitat as the surface became uninhabitable. If we find evidence of life in the Jezero samples, one of the next questions will be whether that life was part of a broader biosphere that extended across an ocean, or whether it was isolated, limited to local hydrology. The answer will tell us not just whether Mars had life, but how much life it might have had. Whether we're talking about a few isolated pockets of microbes in scattered oases, or a thriving planetary biosphere that could have rivaled Earth's in its scope, if not its complexity. The stones remember, but they remember in fragments, in partial records, in clues that we have to piece together like an archaeological puzzle with most of the pieces missing. ALH 84001 gives us a hint that something might have lived in the carbonate depositing environments of early Mars. The Jezero samples will tell us about lakebeds in the late Noachian. Future missions might sample other sites, other time periods, other environments, and slowly, drill core by drill core, meteorite by meteorite, we'll reconstruct what Mars was like when it was young, whether it had an ocean or only lakes, whether life arose once or many times or never at all, whether that life, if it existed, was simple and isolated or complex and widespread, whether it left clear biosignatures we can recognize, or whether it operated in ways so different from terrestrial biology that we might not even recognize its traces without knowing what to look for. These are questions that will take decades to answer, maybe longer. Science moves slowly, carefully, one measurement at a time, but the rocks are patient. They've waited 4 billion years to tell their stories. They can wait a few decades more, and when we finally understand what those stones remember, when we can say with confidence what early Mars was like and whether it harbored life, we'll be ready to address the even stranger question. The question of whether Mars was inhabited not just once, but twice. To understand whether Mars lived twice, we must understand how it lived at all. Every story about life is, at its core, a story about water. Not just because life as we know it requires liquid water to function, though that's certainly true, but because water is rare, special, a molecule that shouldn't be common in the universe, but somehow, against the odds, exists in quantities sufficient to fill oceans and carve valleys and make worlds habitable. On Earth, we take water for granted. It covers 70% of the surface. It falls from the sky. It flows from taps. It's so abundant that we rarely stop to ask where it came from or how it got here. But on Mars, that question isn't optional. It's central to everything. Because if Mars once had rivers and lakes and possibly an ocean, if it had enough water to sustain a hydrological cycle for millions of years, then it needed a source. Water doesn't just appear. It has to come from somewhere. And where Mars got its water, and how much it had, and what happened to it, determines not just whether the planet could have been inhabited once, but whether it could have been inhabited twice. So, where did the water come from? There are two basic possibilities, and they represent fundamentally different stories about planetary formation and the early solar system. The first possibility is that Mars was born wet. In this scenario, water was present in the disk of gas and dust that surrounded the young sun 4.5 billion years ago. Not as liquid, obviously. The temperatures were far too high for that. But as molecules adsorbed onto dust grains, as ice mixed with silicates in the outer reaches of the protoplanetary disk, as tiny particles collided and stuck together, gradually building larger and larger objects, the planetesimals that eventually coalesced to form Mars would have contained water from the very beginning, locked in minerals, trapped as ice in their interiors, a primordial endowment delivered during the planet's assembly. As Mars grew and its interior heated from gravitational compression and radioactive decay, that water would have been released, outgassing from the planet's interior through volcanic eruptions, rising to the surface as steam, condensing to form the first atmosphere, raining down to create the first oceans. Water not delivered from outside, but emerging from within. Mars making its own ocean from ingredients that were present from birth. The second possibility is that Mars was born dry, or at least drier, and that water was delivered later. In this scenario, the inner solar system was too hot during the early stages of planetary formation for water ice to survive. Mars assembled from rocky material, relatively depleted in volatiles. It had some water perhaps, but not enough to create the wet epoch we see evidence of in the geology. The water came later, during a period called the Late Heavy Bombardment. Around 4 billion years ago, perhaps slightly earlier, the orbits of the outer planets shifted. Jupiter and Saturn migrated, destabilizing the asteroid belt and the region beyond Neptune, where comets formed. The result was a cosmic storm. Asteroids and comets rained down on the inner planets for hundreds of millions of years. Earth was bombarded. The moon's heavily cratered surface dates from this period. Mars was hit as well, scarred by impacts that created the massive basins we still see today. And many of those impactors, particularly the comets, were made largely of ice, dirty snowballs, billions of tons each, slamming into Mars at tens of kilometers per second, vaporizing on impact but leaving their water behind. A cometary blessing. Water delivered from the frozen outer reaches of the solar system to a dry inner planet, transforming it into a wet world through catastrophic violence. Both scenarios are plausible. Both are supported by different lines of evidence. And frustratingly, both might be partly true. The question is, which source dominated? Did Mars's water come primarily from primordial outgassing, or primarily from cometary and asteroidal delivery? The answer lies in isotopes, specifically in the ratio of deuterium to hydrogen. Hydrogen is the simplest element, one proton, one electron. It's the most common element in the universe, forged in the Big Bang itself. But hydrogen has a heavy version, deuterium, with one proton and one neutron in its nucleus instead of just a proton alone. Chemically, deuterium behaves almost identically to ordinary hydrogen, but physically, it's twice as heavy, and that tiny difference in mass has consequences. When water molecules escape from a planet's atmosphere into space, the lighter molecules containing ordinary hydrogen escape slightly more easily than the heavier molecules containing deuterium. Over time, as a planet loses water, the remaining water becomes enriched in deuterium. The D to H ratio increases. This means we can use the deuterium to hydrogen ratio as a clock, a measure of how much water a planet has lost over its history. And Mars's D to H ratio is extremely high, about 7 times higher than Earth's ocean water, higher even than most comets. That's the signature of catastrophic water loss. Mars didn't just lose some of its water, it lost most of it, perhaps an ocean's worth, perhaps more. The high DH ratio tells us that ancient Mars had far more water than exists on the planet today. Water that once flowed on the surface, that filled aquifers, that maybe formed that controversial northern ocean. Most of it is gone. Lost to space over billions of years, stripped away by solar wind after the magnetic field failed, leaving only the deuterium-enriched remnant locked in polar ice and subsurface reservoirs. But the ratio also tells us something about where the water came from originally. If all of Mars's water had been delivered by comets, we'd expect the DH ratio, even accounting for loss, to match cometary values. But it doesn't quite. The numbers suggest a mixed source, some primordial water from the planet's formation, some delivered by impacts, a combination. The exact proportions are still debated. Different models give different answers depending on assumptions about loss rates and the composition of the impactors. But the emerging picture is that Mars's water came from both sources. Interior outgassing and external delivery working together to create the wet world of the Noachian epoch. And here's where the two-epoch hypothesis becomes interesting. If Mars had vast reservoirs of subsurface water, aquifers, and ice deposits that survived, the great unmaking, then those reservoirs are ancient, remnants from the first wet epoch, locked away beneath the surface, preserved for billions of years. When volcanic activity heated regions of the subsurface during the second epoch, when orbital variations temporarily warmed the surface, when whatever processes might have briefly restored habitability occurred, they would have been accessing this ancient water, the same water that flowed in Noachian rivers, the same water that filled the Jezero Lake, the same water perhaps that hosted the first Martian life, recycled, remelted, brought back to the surface in a second act. That's a profound idea, because it means the two epochs, separated by billions of years, are not independent. They're connected by the same resource, the same fundamental ingredient for habitability. The water that made the first world possible never completely left. It retreated underground, froze solid, went dormant. But it waited. And when conditions allowed, it could potentially become liquid again, creating brief windows of habitability that echoed the ancient past. This is very different from Earth's water cycle. Our oceans have been liquid and present at the surface for most of the planet's history. Water circulates continuously between ocean, atmosphere, ice, and groundwater, but it's always been part of an active system. Mars's water underwent a phase change in the planetary sense, from active and surface accessible during the Noachian to frozen and buried during the long hiatus, to potentially episodically accessible during brief warming events. It's a cycle that operates on billion-year timescales, a planetary rhythm invisible to any observer who didn't watch for eons. But the water itself, the actual molecules, are the same. H2O with an unusually high proportion of deuterium, a chemical scar that marks everything it touches with the story of loss and survival. There's something poetic about that, about water that witnessed the first rivers and lakes of Mars, then spent 3 billion years locked in ice, then potentially flowed again briefly during volcanic episodes, carrying with it the memory of what the planet used to be. And if life existed during the first epoch, if microorganisms lived in those ancient waters, then their descendants or their dormant spores would have access to the same water during the second epoch. The connection isn't just chemical, it's potentially biological. A single biosphere, if it ever existed, with a timeline that stretches across most of the age of the solar system, not continuously active, but intermittently viable, waking and sleeping with the planet's sporadic warmth. Of course, this assumes life could survive such long dormancy or isolation. That's a massive assumption, one we haven't proven even in principle. But if it's possible at all, if biology can endure billion-year freezes or survive in deep subsurface refugia cut off from the surface, then the shared water. Source means both epochs are part of the same story. The question then becomes not whether Mars was inhabited once or twice, but whether it was inhabited continuously in some form, with surface expression during favorable periods and deep subsurface persistence during unfavorable ones. That's a very different way of thinking about planetary habitability, not as a binary on-off state, but as a spectrum, a world that cycles between obviously habitable, marginally habitable, and apparently sterile, with life adapting its expression to match the conditions. Earth doesn't do this. Our planet has maintained surface habitability continuously for billions of years, allowing life to evolve in complexity from simple cells to the entire biosphere we see today. But Mars, smaller and more volatile, more vulnerable to losing its atmosphere and water, might represent a different class of inhabited world, one where habitability is episodic and life, if present, must be adapted to endure the gaps between favorable periods. This has implications beyond Mars, because as we discover exoplanets and try to assess which ones might be habitable, we tend to focus on worlds that are currently in their habitable zones, that currently have liquid water, that currently have the right conditions. But what about worlds that were habitable in the past and might be habitable again? What about planets that cycle in and out of habitability on timescales of millions or billions of years? Mars might be teaching us that habitability isn't just about the present moment. It's about history, about reservoirs, about the resilience of whatever life might arise. A planet doesn't have to be continuously habitable to be inhabited. It just has to be habitable long enough for life to arise and adaptable enough for life to persist through the unfavorable periods. That greatly expands the range of potentially inhabited worlds, because many planets probably go through phases. Young planets with thick atmospheres that later thin. Planets whose orbits change, moving them in and out of their star's habitable zone. Worlds that experience catastrophic events, impacts, volcanic episodes, stellar flares that temporarily sterilize the surface but don't necessarily kill everything in the subsurface. If life is resilient, if it can wait, then all of these worlds remain potentially inhabited even during their sterile phases. Mars, in this view, becomes not just a case study in how planets die, but in how life might persist despite planetary death. How biology might outlast the surface conditions that gave rise to it, hiding in refugia, waiting for a second chance. And the water, ancient and deuterium enriched, becomes the thread that connects it all, the substance that made the first epoch possible, that sustained subsurface life during the hiatus, that potentially enabled the second epoch's brief windows of surface habitability. Follow the water. That's been the mantra of Mars exploration for decades. It's guided every mission, every landing site selection, every decision about where to drill and what to analyze. But perhaps we should expand that mantra. Follow the water across time. Understand where it came from, how much there was, where it went, where it still exists. Because the water is not just a clue to past habitability. It's the resource that makes present and future habitability possible. It's the connection between epochs, the link between the ancient past and the uncertain present. And understanding Mars's water is understanding Mars's potential to harbor life not just once, long ago, but potentially now, in hidden refugia, and potentially in the future, if conditions ever improve enough to bring it back to the surface. This is planetary science as archaeology and prophecy combined. We're excavating the past to understand what Mars was, but we're also projecting forward to understand what it might become, or what it might still be beneath the frozen surface. The water came from the cosmos, delivered by impacts and outgassed from primordial minerals. It transformed a barren rock into a wet world. It persisted for hundreds of millions of years. It was lost to space and locked in ice. And it might, in some form, still be accessible today. That's the biography of Martian water. And it's also, potentially, the biography of Martian life. Because wherever the water went, life, if it ever existed, would have followed. And through all this science, through the isotope ratios, and the geological reconstructions and the climate models, a deeper question emerges. Not about Mars specifically, not about water or volcanism or orbital mechanics, but about life itself. If Mars was inhabited once, that would be remarkable. If it was inhabited twice, that would change everything we think we know about life in the universe. Not just about Martian life, about all life, about how common it is, about how resilient it is, about what it means for us, here on Earth, looking up at the stars and wondering whether we're alone. Because the difference between one epoch and two is not a matter of degree. It's a difference in kind. A difference that transforms Mars from a tragic story into something far stranger and more hopeful. Let's think about what one epoch would mean. If life arose on Mars during the Noachian, thrived for 100 million years or more while conditions were favorable, then died out completely when the planet froze, that would tell us that life can begin relatively easily. That given the right ingredients, water, chemistry, energy, time, biology will emerge. That's already profound. It would mean life arose independently in two places in the same solar system, on worlds separated by millions of kilometers. That would suggest life is not a fluke, not a cosmic accident that happened once and only once, but a natural consequence of planetary chemistry, something that occurs wherever and whenever conditions allow. The universe would suddenly seem much more alive, not with intelligence necessarily, not with civilizations, but with biology. Microbes in subsurface oceans, metabolic processes exploiting chemical gradients, perhaps simple multicellular organisms in favorable environments. Life, abundant and common, written into the rules of chemistry and physics as surely as stars and planets are. But it would also tell us that life is fragile, that planetary conditions can change catastrophically, that habitability is not guaranteed to last, that a world can support a biosphere for hundreds of millions of years and then lose it completely, irreversibly, leaving only fossils and chemical traces behind. One epoch on Mars would be a story of genesis and extinction. Life emerging from the chemistry of a young wet world, then vanishing when that world transformed into frozen desert. A tragedy on a planetary scale. But two epochs would mean something entirely different. Two epochs would mean that life, once begun, is far more tenacious than we imagine, that it can survive the end of surface habitability, that it can persist through billions of years of frozen silence, waiting in deep refugia or locked in dormancy, that it can re-emerge when conditions briefly improve, blooming again on a surface that was supposed to be sterile. 2 epochs would mean that the great filter that killed the first Martian world didn't kill Martian life. That biology found a way to endure. And if life can do that on Mars, what does that say about life everywhere? This is what philosophers and scientists call the principle of plenitude, the idea that what is possible tends to happen, that the universe is big enough and old enough that anything permitted by physical law will occur, not just once, but many times, in countless variations, across billions of worlds. If life can arise twice on one small, dry planet in the outer reaches of the habitable zone, then it probably arises everywhere that conditions allow. Every wet planet, every subsurface ocean, every hydrothermal system on every moon, orbiting every gas giant in every solar system. The galaxy would be teeming with life, not intelligent life necessarily. That's a separate question with separate filters, but biological life, metabolic life, life that consumes and reproduces and evolves. We would live in a fundamentally biological universe, where chemistry naturally leads to biology wherever the conditions are right, where most rocky planets with water go through a phase of being inhabited, where life is a common feature of cosmic evolution, as natural as star formation or planetary accretion. That's the optimistic interpretation of 2 Martian epochs: life as a cosmic inevitability, biology as a universal phenomenon, resilient and pervasive, adapting to whatever conditions exist, surviving catastrophes, waiting out unfavorable periods, persisting across timescales that dwarf human comprehension. But there's another interpretation, one that's less comforting. Because Mars didn't just lose its surface habitability through bad luck, it lost it because of its size, its position in the solar system, its inability to hold on to its atmosphere once the magnetic field failed. Mars encountered a great filter, a barrier that prevents planets from maintaining long-term habitability, and it didn't pass through that filter intact. It failed. The first world died. If there's a second epoch, if life re-emerged or persisted despite that failure, then we're looking at a partial recovery, a limited renaissance, life clinging to existence in marginal environments, exploiting brief windows of opportunity, never regaining the glory of the wet Noachian when rivers flowed and lakes persisted and the entire planet might have been habitable. That's not exactly encouraging from a cosmic perspective, because it suggests that most habitable planets eventually become uninhabitable, that the conditions that allow life to arise are temporary, that planetary evolution tends towards sterility, and even if life survives, it does so in diminished form, retreating into subsurface refugia, losing the surface environments that might allow it to evolve toward complexity. Earth, in this view, is the exception. The lucky planet that's large enough to hold on to its magnetic field, positioned perfectly in the habitable zone, blessed with a large moon that stabilizes its axial tilt, endowed with active plate tectonics that regulate its climate. But how long will our luck last? Our magnetic field is generated by our molten core, but cores cool. Earth's has been cooling for 4.5 billion years. Eventually, billions of years from now, it will solidify. The dynamo will fail. The magnetic field will collapse. And when it does, we'll be vulnerable to the same atmospheric stripping that killed Mars. The solar wind will begin eroding our atmosphere. The process will be slow. Earth has stronger gravity than Mars, so we'll hold on longer. But the end result will be the same, unless we find a way to prevent it, unless technology allows us to maintain habitability artificially, unless we spread beyond Earth before the filter closes. Mars, in this interpretation, is a warning, a preview of what happens to planets that can't sustain their magnetic fields, a demonstration that habitability is finite, that even worlds that develop life can lose it, that the universe tends toward cold and silence. But here's the question that keeps me awake at night. Which interpretation is correct? Is too epic Mars a promise that life is resilient and common and will find a way to persist no matter what? Or is it a warning that habitability is fragile and temporary and most biospheres eventually fail? Perhaps it's both. Perhaps Mars is showing us that life can survive planetary catastrophe, that biology is more tenacious than we give it credit for, that even worlds we consider dead might harbor hidden biospheres waiting for their moment, but also that surface, habitability, the kind that allows complexity, that permits the evolution of ecosystems and eventually intelligence, is rare and precious and depends on factors largely beyond a planet's control. Earth has been continuously habitable at the surface for billions of years. That's not the norm. That's extraordinary. Most planets are probably more like Mars, with brief windows of habitability separated by long stretches of inhospitable conditions. And yet, even on Mars, life might persist, not thriving, not diversifying into millions of species, but surviving, maintaining a foothold, waiting. That's simultaneously hopeful and sobering. Hopeful because it suggests life is hard to kill completely, that it finds ways to endure that we haven't imagined. Sobering because it suggests that most inhabited worlds might be like Mars rather than Earth, biologically active but not biologically rich, hosting simple organisms in marginal environments rather than complex ecosystems across entire surfaces. The universe might be full of life, but empty of complexity, full of microbes, but empty of anything more sophisticated, full of biology, but empty of minds, unless some inhabited worlds manage to avoid the filters, unless some planets stay habitable long enough for life to evolve complexity, unless intelligence, when it arises, can recognize the filters ahead of time and engineer solutions. That's where we find ourselves, on a planet that has remained habitable far longer than most, with a biosphere that has evolved from simple cells to the entire tapestry of species we see around us, with intelligence that allows us to understand the filters, to recognize the threats, to potentially do something about them. We're in an unusual position, not just alive, but aware, not just surviving, but capable of asking why we're here and what our future holds. And Mars, our neighbor, is the laboratory where we can study what happens when a habitable world encounters a filter, where we can learn whether life survives or perishes, where we can see, written in geology and chemistry and perhaps biology, the story of a planet that was like Earth once and became something very different. If Mars was inhabited twice, it means the story isn't over after the first catastrophe. It means there's a second act, maybe even a third or fourth, playing out over billions of years. It means resilience is possible even when conditions seem hopeless. And maybe, just maybe, it means that when Earth eventually encounters its own filters, whether that's the slow loss of the magnetic field billions of years from now, or the more immediate threats of climate change and ecological collapse, we can learn from Mars. We can see what happens when a planet loses its shield. We can understand the timescales involved. We can appreciate the importance of maintaining the systems that keep our world habitable. And we can choose to act differently, to not let Earth become another Mars. But there's something else Mars might be teaching us, something more subtle and more profound. The too epic hypothesis, if true, demonstrates that the universe is not wasteful, that resources get recycled, that water locked away for 3 billion years doesn't stop being useful. That subsurface aquifers that seem isolated and sterile might be reservoirs of potential habitability, waiting for the right conditions to return. That dormancy is not death. That absence is not extinction. That what appears lifeless might simply be waiting. This is a different way of thinking about the cosmos, not as a place where things arise and flourish and die permanently, but as a place where conditions cycle, where opportunities recur, where nothing is truly final. It's almost biological in itself, the universe behaving like a living system, with periods of activity and dormancy, with resources flowing and recycling, with patterns repeating across different scales. And if that's true, if the cosmos is fundamentally cyclic in this way, then perhaps life is not just common, but inevitable. Not just in the sense that it arises wherever conditions allow, but in the sense that once it arises, it persists, finding ways to survive even when conditions become unfavorable, waiting for the universe to cycle back around to states that permit activity. Mars might have been inhabited 4 billion years ago and uninhabited for 3 billion years. But if it's inhabited again now in any form, whether through microbial life in the subsurface, or through seasonal activity that flickers with volcanic warmth, or even through dormant organisms waiting to revive, then the 3 billion year gap is just a pause, a breath held between exhalations. The story didn't end. It just entered a different phase. And if we find evidence of this, if we confirm that Mars hosts life today that traces back to the Noachian epoch, that survived the great unmaking, that persisted through the long hiatus, we'll have discovered something extraordinary. Not just life on another planet, but life that has endured across timescales we can barely comprehend. A biosphere older than most of the craters on Mars. A lineage that traces back to when both Earth and Mars were young and wet and full of possibility. We would be looking at our siblings. Life that arose in the same era as terrestrial life, in the same stellar neighborhood, from the same raw materials delivered by the same cosmic processes. Life that diverged from ours, not in chemistry or heritage, but only in circumstance, shaped by a different planetary fate. And we would have to reckon with what that means, for our place in the universe, for our understanding of biology, for our assessment of how common or rare life actually is. One example of life, Earth, tells us almost nothing. It could be unique, it could be common. One data point doesn't make a pattern, but 2 examples, arising independently in the same solar system, surviving through different pathways, persisting across eons. That tells us something profound. It tells us we're not alone, not in the sense of intelligent neighbors who might respond to our messages, but in the deeper sense of biology as a cosmic phenomenon, life as something the universe does, not just once, but routinely, wherever and whenever conditions allow. It tells us that the universe is alive, that we live in a biological cosmos, that the stuff of stars and planets naturally organizes itself into living systems, not as a rare miracle, but as a common expression of chemical and physical law. And it tells us that life, once begun, is extraordinarily hard to eliminate completely, that it finds ways to persist that we're only beginning to understand, that the line between living and dead is blurrier than we thought, with dormancy and subsurface refugia representing states that we might not recognize as life, but that retain the capacity to become active again when conditions permit. Mars is not just a neighbor in space, it's a mirror, reflecting back to us possibilities about what life can be, how it can persist, where it might hide, how resilient it might prove against the filters that threaten all inhabited worlds. And perhaps Mars is also a message, written in stone and ice and thin air, a message about survival, about patience, about the long game that biology plays across timescales measured in billions of years, a message we're only now learning to read. Perhaps Mars is not just a neighbor, perhaps it is a message. There is a world visible in our night sky that almost made it, almost became a second Earth, almost sustained its rivers and lakes and oceans for billions of years instead of hundreds of millions, almost kept its magnetic shield and thick atmosphere and warmth, almost. But the margin between almost and actually is measured in planetary physics, in core temperatures and gravitational constants, in distance from the sun and the accidents of formation that determine whether a world is born large enough to hold on to what it creates. Mars was too small, or too far, or too unlucky. And so, It fell silent. But perhaps not completely, perhaps not forever. That's what makes this story different from a simple tragedy. Because if the evidence we've explored is real, if the methane pulses are biological, if subsurface life persists in hidden aquifers, if volcanic episodes temporarily restored surface habitability, if dormant organisms wait in ancient ice for conditions to improve, then Mars didn't die. It transformed from a world where life existed openly, on the surface, in the light, to a world where life became hidden, subterranean, patient, adapted not to thrive, but to endure. And endurance across 3 billion years is its own kind of triumph. We tend to think of life as something vigorous, growing, spreading, diversifying. The explosion of forms we see on Earth, from bacteria to blue whales, from fungi to forests, life filling every available niche with exuberant creativity. But maybe that's just one expression of biology, the expression that happens on worlds that stay habitable long enough for complexity to emerge. Mars might be showing us a different expression, life as persistence, life as patience. Life that waits in darkness, metabolizing so slowly that time itself becomes meaningless, preserving the basic machinery of biology across eons, neither thriving nor dying, but existing in a state between. That's not the life we recognize easily. It doesn't look like success from our perspective, but it's survival nonetheless. And if life arose twice on Mars, or if it survived from the first epoch to the second, then we're witnessing something that changes the entire conversation about biology in the universe. Because it means life is not fragile, not easily extinguished, not dependent on continuous favorable conditions. It means life is tenacious, adaptable, capable of finding ways to persist that we haven't imagined because we've never had to. We've lived on a world that stayed habitable, so we've never developed the survival strategies that Mars would require. But Martian life, if it exists, has had billions of years to develop those strategies. Billions of years to learn how to survive cold and darkness and isolation and the slow decay of the world around it. What we might find when we finally drill deep enough or sample the right deposits might not look like Earth life. It might be so adapted to survival, so stripped down to the essentials, so alien in its strategies that we'll struggle to recognize it as life at all. Or we might find that the fundamentals remain the same, DNA or something like it, proteins, lipid membranes, the basic architecture of cells preserved across 4 billion years of divergent evolution, because some solutions to the problem of being alive are universal. Either way, we'll learn something profound about what life can be, about the range of conditions it can tolerate, about the time scales over which it can persist, and we'll learn something about ourselves, about our own resilience or lack of it, about whether we could survive if Earth underwent a similar transformation, about what strategies we might need to develop if we're to persist beyond the lifespan of surface habitability on our own world. But there's another lesson here, one that's harder to articulate but perhaps more important. Worlds are precious. Mars was habitable once. It had rivers and rain and skies that might have been blue or gray or some color we can't imagine. It had the potential to become something extraordinary, and then it lost that potential, not through anything it did, not through choices or mistakes, but through the simple physics of being too small to hold onto its atmosphere. Once the magnetic field failed, Earth could lose its habitability too. Not in the same way. We're larger, our dynamo should last billions of years longer, but in other ways we have more control over. We can alter our atmosphere. We can disrupt the climate systems that keep our world temperate. We can exhaust the resources that our biosphere depends on. We can, through action or inaction, transform our planet into something less habitable, not into Mars. Earth won't freeze and lose its air the way Mars did, but into something diminished, something where the margins for life are narrower, where ecosystems collapse, where the abundance we take for granted becomes scarcity. Mars is a reminder that habitability is not guaranteed, that the conditions that allow complex life to flourish are rare and precious and depend on factors that must remain in balance, and that once lost, habitability might not return for billions of years, if ever. So perhaps the lesson is both cosmic and immediate. Cosmic in showing us that life might be common, resilient, pervasive across the universe, arising wherever conditions allow, and persisting through catastrophes we can barely imagine. But immediate in reminding us that the life we know, the rich, complex, beautiful biosphere of Earth, depends on maintaining the conditions that support it, that we live on a rare world, one that has remained continuously habitable for billions of years, and that this is not the norm, but the exception. Mars almost was what Earth is, and Earth could become what Mars is if we're not careful. If we don't recognize the value of what we have, if we don't act as stewards of the only world we know for certain is alive. The red sands of Mars stretch for thousands of kilometers under skies the color of rust. The wind blows, raising dust devils that spiral upward and dissipate. The ice caps gleam at the poles. The ancient riverbeds cut through highlands that remember water. And beneath it all, perhaps, in darkness and silence, life waits for warmth, for water, for another dawn. Or perhaps not. Perhaps Mars is truly dead, and we're seeing only the ghosts of what once was, reading meaning into methane pulses and water-car valleys because we want so desperately to find life beyond Earth. But even if Mars is sterile, even if no biology survives there, the planet still teaches us what we need to know, that worlds can change, that habitability is temporary, that the conditions we depend on are more fragile than we imagine, and that every world that lives briefly in cosmic terms. So, we should be grateful for our magnetic field and our atmosphere and our oceans, for the accident of formation that made Earth large enough and positioned it perfectly, for the 4 billion years of continuous habitability that allowed life to evolve from simple chemistry to everything we see around us. We should be grateful, and we should be careful, because we live on a world that almost was Mars and stayed Earth instead. And the difference between almost and actually is everything.